In the third segment, let us look at this molecule which I have uh, drawn in this slide. In this are the hydrogen atoms on the methyl group symmetrically equivalent or not, and methyl group illustrate important aspect of symmetry. Occasionally, one or more portions of the molecule exhibits what is referred to as localized or local symmetry as opposed to the global symmetry. So I'm now introducing a concept called as a locally they are symmetric, but globally they may not be symmetric. So local symmetry applies to just a small portion of the molecule. By virtue of their structures, most methyl groups have free rotation about the CC bonds connecting them to the larger molecule. The CC bond is coincident to a local symmetry axis of rotation C3, which renders all the three hydrogen atoms symmetrically equivalent to one another. Okay. How many different equivalent sets of hydrogen atoms are found on the following molecule? So the C3 axis is there, and each rotation being 120, and the answer is 3. Okay, so 3 sets of that. Notice that because of the local axis of rotation, all the 3 methyl groups are equivalent, and hence all the 9 methyl hydrogen atoms are equivalent, and they all form only one set. Okay, the 2 hydrogen atoms on the methylene carbon are equivalent and they form a second different set, while the aldehyde CHO hydrogen forms the third set. Now, in proton NMR spectroscopy, when looking for symmetrical hydrogen group, will it typically be simpler than the previous example? How many equivalent hydrogen sets exist on each molecule below? You can just see, and we will see the NMR. Okay, so 3 peaks, 3 unique hydrogen sets. You just compare with this, and then here 1 peak, 2 equivalent hydrogen sets. Let us go to the IR spectroscopy. I have given the different functional groups that can be found with respect to the wave number and transmittance. So it is used as a fingerprinting, and in many cases it is also used to derive the structure. So fingerprinting region is there. Fingerprinting region, and you can plot it in terms of nanometer wavelength or wave number centimeter inwards. So NH, OH, CH, C triple bond and C triple bond C, C double bond O, C double bond and C double bond C, etc. So carbon 13 NMR spectroscopy. So what information it will provide to us? It will provide the functionality based on the chemical shift. It tells the type of carbon by a position of the signal on the x-axis. It also tells presence of symmetry via the number of signals. It also tells us the presence of non-protonated carbons via small signals, sometimes useful, but not always. What are the typical chemical shifts in C13 NMR spectrum? That 190 to 220 delta, you see aldehyde and ketone. 160 to 190 delta, esters, amides, carboxylic acids, acyl halides. 110 to 160 delta, arenes, alkenes, etc. 50 to 110 delta, alkynes, sp3 carbons attached to functional groups. 0 to 50 delta, sp3 carbon and sp3 carbon linkage, wherein tertiary is greater than secondary, greater than primary. What is the proton NMR information provided? Again, the same functionality, presence of symmetry, number of protons, and number of neighboring protons. Okay. And what are the typical chemical shifts? 10 to 12 carboxylic acid, 9 to 10 aldehyde, 6.5 to 8.5 aromatic, 5 to 6.5 alkene, 2 to 4.5 alkyne, and 0 to 2 sp3 carbon attached with hydrogen. And typically tertiary is greater than secondary, greater than primary. Symmetry and equivalence. There are 8 hydrogen atoms in this molecule, which I have described in this, and we see only 3 signals because they are all equivalent. Number of signals is equal to number of different types of hydrogen atoms present. There are 3 different signals because the hydrogens are in 3 different environments. Okay, now let us go to the Raman spectroscopy, which are not widely being taught and extensively being discussed to the students. The overview about the Raman is it is a vibrational spectroscopy. IR and Raman are the most common vibrational spectroscopies for assessing molecular motion and fingerprinting species. Based on the inelastic scattering of a monochromatic excitation source, Raman spectroscopy operates based on inelastic scattering of a monochromatic excitation source. What is the energy range routinely involved is 200 to 4000 centimeter inverse. What is the complementary selection rules to IR spectroscopy? Selection rules dictate which molecular vibrations are probed, and sub-vibrational modes are both IR and Raman active. Great for many real-world samples, Raman spectroscopy. It is a very, very minimal sample preparation. Sample preparation is not very difficult. You can take a gas, liquid, solid, etc., and compatible with wet samples and normal ambient conditions. There are no very big difficulty. So both IR and Raman are used as a fingerprinting, but only difference in IR, we plot the transmittance or the absorbance versus the wave number. But here we plot the delta sigma, that is the change. We are seeing the Raman shift, that is centimeter inverse, and the Raman signal intensity. From where these things come, we will just look into that. And group assignments identify characteristic vibrational energy. So we are making use of delta sigma, which is centimeter inverse, which x-axis of Raman spectrum always is Raman shift in centimeter inverse. Okay. In this table, I have given the typical fingerprinting regions of various functional groups that one can encounter in an organic molecule. And how do we treat it? Classical treatment is number of peaks related to the degrees of freedom, which is 3n minus 6 if it is a bent molecule, 3n minus 5 if it is a linear molecule for a molecule consisting of n atoms, and energy related to the harmonic oscillator. This you teach to the students. Selection rules related to the symmetry rule of the thumb, symmetric Raman active, asymmetric IR active. Okay. So like IR, you can also have an expression for Raman. Delta sigma is equal to C by 2 pi square root of K M1 plus M2 divided by M1 M2. Okay. So we will compare the carbon dioxide, which is a linear molecule, versus the water, which is a bent molecule. So Raman, you see 1335 centimeter inverse for carbon dioxide. IR, you see 2349. And another IR band you are seeing at 667 centimeter inverse. Whereas here, all the modes are both IR and Raman active. That means if you are recording IR and Raman, you don't have to record both. If you record one, that's more than enough for water, because it is going to be the same in the IR also or in the Raman also. Okay, so that distinguishes the structure. What is the main optical transitions? Absorption, scattering, and fluorescence. When you are shining a laser, usually Raman spectrum is recorded using a high energy laser. Why we need high energy is Raman spectroscopy is based on the scattering technique. So it is not a transmitted one, it is not a absorbance one, it is a scattered one, and therefore to collect the scattered rays, one has to use a really high energy radiation. Then only you will get at least some information on the on your molecule. So when you are pumping the laser, you can have fluorescence. There can be any number of things that can be happening. So elastic scattering, that is the Rayleigh scattering, that is going to whatever that it is going to absorb, it is going to throw. And then fluorescence, it is going to go to the singlet to singlet and singlet to triplet and coming down. So all these kind of complications are there, and we will try to look into that. I mean, what is it that we are doing in IR? We are measuring only the sigma. Okay, that is a frequency. Okay, and 0 to 4000. But in Raman, we look at the Stokes and the anti-Stokes, that is plus or minus delta sigma. Raman means delta sigma is sigma emitted minus sigma. This is what we look at it. And there is also a technique called as a resonance Raman, which is a sigma emitted minus the sigma. Okay, so that is also a kind of an information one can get. Okay, and you can use a 785 nanometer laser, you can use a 514 nanometer laser, and so 785, when you are using Stokes, is on the left hand side minus delta sigma, and anti-Stokes is on the right hand side, and Stokes and anti-Stokes is on the right hand side in the 514 nanometer laser. This is again the same picture that I am showing about the. This I am trying to highlight that when you are doing a Raman, you will always encounter some amount of problem from the fluorescence of the molecule. If your molecule is going to be fluorescent, you have to be very careful. You have to record the spectrum minimum 10 to 15 times. Like you do in your FTIR spectrum, you tell that I need a 16 scan, 32 scan, 64 scan. In Raman also, you should not do only one scan and get the spectrum and start interpreting the data. You should do minimum 6 scans or 12 scans, because you have to take care of the interference from the fluorescence, which is a big trouble in Raman. That will mask your Raman signals. Okay. Raman is a vibrational spectroscopy akin to infrared. It is good for fingerprinting, probing molecular symmetry. In fact, if you ask me, this is a much more better technique, better technique to probe the overall symmetry, global symmetry and the local symmetry. It gives information about the local symmetry and the global symmetry. It is a scattering based and not a transmission or a reflection, means no need for fancy sample preparation. You can do on gas, liquid, solid. Virtually always use anti-Stokes line due to stronger signal. We don't use the Stokes line. And you need to pick excitation energy, laser line, 785 nanometer, fluorescence less probable. Low, but you will get the intensity of the Raman low. 514 nanometer, fluorescence more probable, but resonance also more likely, but you will get a very strong signals. So you have to optimize the conditions to collect the right set of signals with good intensity for interpretation. Other things which I am not talking today is the surface enhanced Raman spectroscopy. That is a separate topic on itself, and quantum origins of selection rules and scattering cross sections. I am not discussing that. Let us also look into the dichroism. What is linear dichroism? Difference in absorption, parallel versus perpendicular polarized light. So that is called as a LD. Optical rotatory dispersion, that is ORD, rotation of linearly polarized light by the sample. Circular dichroism, which is CD, difference in absorption of left versus right circularly polarized light. This spectroscopy technique is quite useful in biological molecules, in biology also. So polarization of light, the light is unpolarized as shown in the left hand side of this, and you can force it to travel in only one direction. That means it is a linearly polarized light or the plane polarized light, and you can make it to rotate. That means it can be moved to the left or the right, and that is a circularly polarized light. I have just shown you that. Okay, direction of propagation of this light. So polarization of the light consists of two circularly polarized components of equal intensity by opposite sense of rotation. The two components are like left and right-handed helices. Two orthogonal plane waves with a 0-degree phase difference from linearly polarized light, two orthogonal plane waves with 90 degrees phase difference from a circularly polarized light. So depending on whether the phase difference is plus or minus 90 degrees, the sense of rotation is determined to be clockwise or anti-clockwise. So differential absorption of the clock and the anti-clockwise components by an optically active compound results in a rotation of the plane of the light. Okay. So here I have distinguished the linearly and circularly polarized light, and superposition of plane of polarized light. That's what we record in CD, circular dichroism. So these are all some of the superpositions which can be possible when you are, using a plane polarized light. So differential absorption of two circularly polarized beams, then you get a signal. Okay, let us see that. And this technique is based on the Cotton effect. The differential absorption of circularly polarized light changes its sign in the region of maximum absorption. So ORD spectra are also again dispersive, like a scattering. Here it is a dispersive spectra, ORD. But CD is an absorptive spectra, and therefore you will not lose any information. You will get a very clear cut, information. So it also, like a Stokes and anti-Stokes, it is also working on a positive Cotton effect and a negative Cotton effect, and the difference that we see it in the signal. So optical rotatory dispersion, the angular velocities of the left and right circularly polarized beams are different in the sample. The orientation of the ellipse is called as a optical rotation. Okay, it is the orientation of the ellipse. The measurement of the optical rotation in dependence of the used wavelength is the optical rotatory dispersion. In circular dichroism, in substances with optical activity, the left and right circularly polarized light beams are traveling at a different speed and are absorbed to a different extent. So the circular dichroism is characterized by the ratio of the semi-minor and the semi-major axis of the ellipse. So usually we call this as tan theta is equal to C by B. Theta is known as a ellipticity. Okay. Now towards the end we have reached, and I'm going to give you the various glossary of spectroscopic and structural techniques. Atomic absorption spectroscopy, its description is electronic spectra of atoms in flames. Application is elemental analysis. Atomic OJ electron spectroscopy, AES, velocity spectra of secondary photoelectron ejected from solids after absorption of high energy radiation. For what it is used, study of solid surfaces giving identity of atoms and information about their local symmetry. CARS, that is coherent anti-Stokes Raman spectroscopy, let us not deal, that is a little higher level. Circular dichroism, what is the description? Study of difference in the absorption coefficients for left and right circularly polarized light, studying optically active species, particularly complexes of transition metals. Majorly it is used in biological molecules. Chemical ionization mass spectrometry, and we also use under NMR, many two-dimensional NMR techniques, COSY, correlation spectroscopies. That is, we try to find out whether the protons are talking with each other, whether the carbons are talking with each other, and CP mass, that is NMR spectroscopy, that is cross polarization magic angle spinning. This is used for the solids. Solid state, you can record the NMR. And what is the application? Important for C13 NMR spectra of solids, useful for many other nuclei also. Okay. Let us go to the depth. There are a lot of NMR advancement that has taken place. Dante, depth, and 2D NMR, that is useful in analyzing complicated 1D NMR spectra and determining the connectivity in unknown structures. Electron diffraction, that is not part of today's lecture. EDX, EDX is the X-ray fluorescence of a solid sample when bombarded with energized electrons. What is its use? Used in electron microscopes, often in conjunction with yields, energy electron loss spectroscopy as an analytical tool. So energy electron loss spectroscopy is an inelastic scattering of electrons from gas or molecular beam samples. Electronic vibrational spectra, particularly important in studies of surfaces by electron microscopy. Electronic spectroscopy, as you are fully aware of that, absorption or emission of radiation, usually in the visible and UV regions, accompanied changes in the electronic state. Electronic energy spectra, which will detail both the upper and the lower energy level states in your molecule. Electron microscopy, that is not the topic of today's discussion. EPR, electron paramagnetic resonance spectroscopy. Another name is electron spin resonance spectroscopy, particularly applied to radicals in gas phase or in molecular beams. And for solids also, you can use it to determine the paramagnetic species and its local symmetry. ESCA, that is electron spectroscopy for chemical analysis, another name for X-ray photoelectron spectroscopy. And EXAFS, that is extended X-ray absorption fine structure. So what is its use? Its use is to understand the atomic distances, distribution of interatomic distances around atoms of the element in the solids, liquids, solutions, surfaces, etc. Fluorescence spectroscopy, you can use UV light or visible light and you can study the fluorescence. FTIR, I have projected to you, and we are having these are all additional things which are related to the NMR and other things, inept, inadequate, INDAR, HOHA, and HOISI, Hector. All these things are further advanced techniques to find out the structure of molecules. Infrared spectroscopy, I have dealt with you. Mass spectrometry, today I have not dealt, but mass spectroscopy is another technique which you are going to make use of to understand what is the molecule from the fragmentation pattern, what is the structure of your compound. It can also give you bond dissociation energies, etc. And you can advance that technique using a matrix isolation. And you nowadays even magnetic circular dichroism is being used. That is whether the magnetic field is inducing the left or right cotton effects. That is also being used. And microwave spectroscopy is becoming a very powerful technique. And Moss wire spectroscopy, at least in our country, there are not many people who are into that. And MS technique is two different mass, and that is going to be a very powerful tool. So I have listed all these different spectroscopy techniques. In this Raman, we have dealt with it. Photoelectron spectroscopy, we have dealt. Optical rotatory dispersion, we have dealt. We have not dealt in detail about the NQR, that is the quadrupolar things that are not being done in our country now. So NOSI, COSI, all those things, you are fully aware of that. And rotational spectroscopy, we have dealt. UV visible spectroscopy, we have dealt. And ultraviolet photoelectron spectroscopy, I have indicated to you what information that it can give. It can give the band shapes, in bonding, non-bonding, anti-bonding character of the levels. So you can use vibrational spectroscopy. In addition, you can also use X-ray diffraction. And I have listed the references which I have used to prepare these lectures. So I feel these will help you